Hello class, in this video we're going to be looking at balancing chemical equations. The learning intention for this video is we're going to understand what happens at the atomic level during a chemical reaction and how it can be represented in various ways. We're going to understand what it means to balance a chemical equation, to understand why we have to balance chemical equations, and to also practice balancing chemical equations. Now, the first thing we're going to be looking at is what is a chemical reaction. Now, in a chemical reaction, what actually happens at the very atomic level is that the actual particles rearrange themselves differently so that they can actually form new products. So new products meaning new substances. Now, to make this work, what actually happens is that the chemical bonds that were initially present in the starting materials, they actually get broken up and new bonds are actually formed when particles rearrange themselves, resulting in new substances. So if you actually look at this particular GIF over here, notice that you've got two separate molecules, but when this molecule keeps in contact with this one over here, the bond between the green particle and the blue particle, they essentially get severed, and as a result of these, they now form a new substance, this substance over here, and another substance gets ejected. So this is what happens in a chemical reaction, and this is also summarized on the right hand side over here as well. So if you look on the right hand side over here, some of the chemical reactions that you might see is when you've got two particles and they merge together to form a new substance. That could be one, and that's an example of a chemical reaction. Another example of a chemical reaction is where you've got one huge molecule or compound, and what happens in the chemical reaction is that the individual atoms, they actually separate from one another. You therefore create a new substance in this case, and that's why this is an example of a chemical reaction. And for the most chemical reactions that you actually see, the more complex ones, what actually happens is that the two pairs of substances, they actually exchange their substituents or their atoms. As a result, you can see that this orange atom over here now pairs up or is bonded to the green atom. So now this forms a compound, a new compound, which is why this is an example of a chemical reaction. So I'm going to show you again using my simulation over here, just show you what actually happens during a chemical reaction. So we've discussed already that in order for a chemical reaction to occur, chemical bonds need to be broken so the particles then can therefore rearrange themselves to form new bonds, in doing so creating new substances. So notice in this particular example over here, I've got two molecules of hydrogen gas. Now if I introduce one molecule of oxygen gas, which contains two oxygen atoms bonded to each other, what happens is that if I want these molecules to react together, what actually happens is that the bonds between each of these atoms, they actually get broken up. And once these bonds broken up, then the actual atoms can then rearrange themselves and form new bonds. So now that the bonds are broken, oxygen will now form a bond to two hydrogen each, and notice that they now form a new substance. In this case over here, I'm hoping that you guys recognize that the new substance formed in this case is water. So you've actually produced two molecules of water in this case, and the chemical reaction can therefore be summarized in this worded format. So you've got hydrogen gas plus oxygen gas, and this produces water. And again, just to note, the straight line in this case just represents the chemical bond that holds these atoms together. Now, the common misconception that students often think is that during a chemical reaction, they believe that atoms change the actual elements during a chemical reaction. So to describe this incorrect conception, what I have over here, I've got two molecules of hydrogen, I've got a molecule of oxygen. Now they think in a chemical reaction the actual atoms change to another type of atom. In this case over here, you've got sodium atom and you've got helium atoms. This cannot be true at all, because whatever you have at the beginning, if you've got a hydrogen atom, you cannot miraculously come up with another type of atom at all, because obviously different elements have different number of protons, electrons, and neutrons. They can't just somehow gain these number of protons to form these new elements. So don't make this mistake over here. So what I have over here is I've said you cannot start off with hydrogen, oxygen, and end up with different atoms in the product. Okay, so just make sure you're not making this same mistake as well. Now that we've talked about chemical reaction, we can actually illustrate or display these chemical reactions in three different ways. We can do this by using a worded equation, which I've shown you previously. So I could write methane plus oxygen, and what this does is this yields, so this arrow over here means yields or produces carbon dioxide, and water. I can also show this diagrammatically or structurally. So that what I mean is that you actually show the actual bonds and show how are the actual atoms within the actual substances or molecules are rearranged. So in this case over here, using the exact same chemical equation above, you've got methane, which is CH4. Notice that 4 of the hydrogens are attached to the central carbon. You've got oxygen gas over here, and you've got carbon dioxide as well as water. So that's what I mean by showing it structurally. And lastly, you could also show this using chemical symbols, so using this shortened abbreviated notation. Now, for the purposes of the year 10 chemistry curriculum, you're not really required at all to know how to draw things structurally. That's more year 11, year 12 stuff. But for now, the only things that you really need to know is how do I write a chemical reaction using words, so the first option, as well as using it, writing it using actual chemical symbols. So the reason why we actually use the chemical equation more readily, or we prefer that as opposed to the worded equation, is firstly, notice that this is a lot more shorter and abbreviated as opposed to this long sentence over here. So the first reason why we use a chemical equation, because it simplifies and condenses the worded equation. Not only that, but it also provides you the chemical formula of each reactant and product. So what I mean by reactant is that's just the starting material. So you've got methane and you've got oxygen, and it also shows you the chemical formula of the products as well. In doing so, what it tells you is it tells you what atoms is present on for each reactant and how many atoms are also present as well. In addition to this, notice that you've actually included states in your chemical equation. So notice that in my worded equation, I don't actually know whether it's in a solid state, whether it's in a liquid state, or whether it's in a gaseous state. Whereas in my chemical equation, this information is also provided for me as well. And lastly, the really good thing about a chemical equation is that it also provides the ratio for that given chemical reaction to occur. What I mean by that is, do you need a 1-to-1 ratio? So one substance reacts with one substance. Does that result in a chemical reaction? Or do you need one reactant with another 2 other different type of reactants in order for the reaction to proceed? That's what I mean by the actual ratio itself. What we're going to be looking at now is we're going to be interpreting chemical equations. So firstly, we said a chemical equation shows the chemical formulas of a reactant and products. On this particular slide over here, I've actually shown you the definitions of a reactant and product. So as I said, reactants are the starting materials that undergoes a chemical change, and they are always going to be displayed on the left-hand side of a chemical equation. So all of these substances over here, these are my reactants, whereas anything written on the right-hand side of the chemical equation is referred to as the products, and these are the substances that are formed at the end of the chemical reaction. Now, the common misconception is that students often think that in a chemical reaction, one particle reacts with one particle, resulting in a chemical reaction. That's not necessarily true at all. So not all reactions occur in a 1-to-1 ratio. Some might occur in a 1-to-2 ratio, as displayed in this example over here. So in this example over here, you've got CH4. So this is methane over here. The white atoms in this case, that represents hydrogen. The black represents carbon. The red represents oxygen. So you can see that there are, in order for this chemical reaction to occur and form these products, in order for it to form CO2 as well as water, you need to have 1 molecule of methane with 2 molecules of oxygen in order for this to occur. If you only had 1 molecule of methane and 1 molecule of oxygen, a chemical reaction will not occur at all. So therefore, if I was to display this using a chemical reaction, chemical equation, I would actually need to denote this 2 over here. So on my next slide over here, I'm actually showing you that in a chemical equation, we actually need to show the coefficients. So the coefficient is actually inserted or placed in front of the actual molecule just to state how many molecules are required for that reaction to proceed. So as shown in the diagram, you need 1 molecule of methane with 2 molecules of oxygen gas, which is why I've got a 2 over here. Notice I've also got a 2 over here because I'm actually forming 2 molecules of water for every 1 molecule of methane and every 2 molecules of oxygen. So in this slide over here, just the main thing that I want you to understand is the difference between a coefficient and a subscript. The coefficient is the number in front of the molecules, and sometimes we need to insert this for our chemical equation, sometimes you don't see a coefficient at all. So for instance, if you don't see a coefficient like the ones that you have over here, that's just implied that there's a 1 in front, but we generally don't write the 1 at all. And a subscript is pretty much the lowercase numbers over here. So in this case, this 2 over here, these lowercase numbers indicate how many numbers or how many atoms are present for that particular substance. So the first question reads out, how many hydrogen molecules are required to react with oxygen to produce water? So I've got the diagram as well as the chemical equation just to illustrate for you guys right now. Now notice over here, the blue atoms in this case, this represents your hydrogen gas. So each of this, that's one hydrogen gas molecule, that's another hydrogen gas molecule. This is also represented by your chemical equation here with the coefficient 2. So to answer this question over here, because it's asking how many hydrogen molecules are required to react with oxygen, in this case over here, you require 2 molecules of hydrogen gas. So all we're doing is just interpreting it from our chemical equation. So the second question over here, or the second example reads, how many hydrogen atoms, so this is different from molecules, how many atoms are present in the actual reactants? So how many, so in order to actually answer this question over here, what you could actually do is you could actually draw up the actual molecules itself just to aid with your understanding. So if I also do this, notice that this 3 over here indicates there are 3 groups or 3 molecules of hydrogen. If I was to display this diagrammatically, notice that in this case over here, you can actually see that there are 6 hydrogens in total. But obviously you don't need to actually draw this out. This is just for you guys just to understand it. But what you could do is, this is pretty much the same thing as writing 3 multiplied by 2 in this case over here. So that's another way that we could actually arrive to the same answer. So you've got 6 hydrogen atoms in total. We're now going to be moving on to the second part of today's lesson, which is about balancing chemical equations. So what is balancing chemical equations? So firstly, let's think about, what does the word balance mean? So I've got a balance or a scale over here, and from your own understanding, you should agree with me that the word balance just essentially means when something is actually even, or when something is equal to one another on both sides. So that's what balancing is. So if we were to use this definition or this word in the chemistry sense, when we're balancing chemical equations, what this means is that there are the same number of each type of atom present on both sides of the equation. This is what we mean when an equation is balanced. So essentially, if you got the same number of elements on the left-hand side as well as the right-hand side, this equation is now considered to be balanced. Okay guys, I've got an example over here to show you why this particular chemical equation is said to be balanced. So when we're trying to test whether an equation is balanced, what we're trying to do is we're trying to see whether there is the same number of atoms of each element present on both the left-hand side as well as the right-hand side of the equation. Now, this is not something that you generally have to do at all, but because we just started learning about balancing chemical equations, what we generally need to do is we need to set up our working out something similar to this over here. So on the left column over here, what you do is you actually list down all the elements present in the reaction. And on the second column, you've got the reactants, which tells you the number of atoms for each of those atoms. And on the right-hand side, you've got the products. So in this case over here, what I'll do first is I'm going to list down all the different unique elements or atoms present in this reaction. In this case over here, I've color-coded it. So there's only carbon, hydrogen, and chlorine. So these are the only elements that's present in this chemical reaction. What I'll do next is I need to count down how many carbon atoms are there present in the reactant. So the reactants meaning on the left-hand side. In this case over here, there's only 1 carbon atom. For hydrogen, there's only 4. For chlorine, we can see that in this case, there's 2 over here, but notice that you've got a 4 in front, meaning we need to multiply because there's 4 molecules of chlorine, and therefore this is going to be 8. We now do the exact same thing on the right-hand side. So how many carbon atoms are there on the right? We can also see there's 1. For hydrogen, we also see there's 4, because 4 times 1 is 4. And for chlorine, we can see that there is going to be 4 chlorines plus another 4 here as well, because we have to multiply that coefficient by everything in that molecule. So therefore, that would also equal 8. Now, when the numbers for each single atom is the same, we therefore consider this type of chemical equation to be balanced. Now this particular example of here is just slightly more difficult than the other one before, but again using the exact same principles. So if we're testing to see whether something's balanced, again we need to show our working out in this particular table over here, list down all the elements, and then start counting how many atoms are there on the left hand side and right hand side. So we can see that for this particular example, there are 3 carbon atoms. Now there's also 8 hydrogen atoms on the reactants as well. For the number of oxygens, we can see that there is a coefficient of 5, so we need to multiply 5 with the subscript 2, which therefore gives me 10. So there are 10 oxygen atoms in total on the left-hand side. Let's start counting the number of atoms on the right-hand side. So for carbon, we can see that there is 3. For hydrogen in this case, we'll multiply 4 with this little 2, so therefore this gives me 8. And notice that you've got 2 products over here, but each of these products have their own oxygen atom. So in order to count the total number of oxygens, what I need to do is find how many oxygens is present in water, how many is present in carbon dioxide, and just add them up in total. So in this case over here, I want to multiply 4 with 1, which gives me 4. So this has 4 oxygen atoms in total, whereas this has 3 times 2, which is 6. So I add 4 and 6. Therefore, this gives me 10. Now, what I need to do is I need to check whether these numbers over here are the same. In this case over here, they are the same. So this indicates that this particular chemical equation is balanced. Okay, now it's time for you guys to actually see yourself whether this particular chemical equation shown below is balanced or not. So I'm going to give you about 3 minutes, although I don't think it takes 3 minutes at all to actually answer this question. But take your time answering this question. Please pause the video right now and complete the following table, and then press the play button to see whether your answer matches my answer. Now, in this case here, we can agree that the number of sodium atoms on the left-hand side is 2. Fluorine is also 2. I want to find out how many atoms are on the right-hand side. This is 2 as well because I multiply 2 with 1, and 2 times 1 over here is also 2. So therefore, in this case, since I can see that the number of atoms for sodium and fluorine is the same for the reactants as well as products, therefore this particular equation is balanced. Again, similarly, please pause the video right now to see whether this chemical equation is balanced or not. So in this case over here, we can see that there are 2 potassium atoms on the left-hand side. There's 4 iodine atoms on the left-hand side. Find out how many atoms are there on the right-hand side. In this case, 2 times 1 is 2. So there's 2 potassium atoms. So in this case, the potassium atoms are balanced, but in this case of here, there's only 2 atoms of iodine, and because these numbers over here do not equal with one another at all, although these are equal, this particular chemical equation is not balanced, or it's unbalanced in this case. And for my final example, just to see whether this particular chemical equation is balanced, please again try to pause the video and see whether your answers are aligned with my answer. So we're going to do the exact same thing, just count the number of atoms present. So we can agree that there are 2 sodium atoms on the left hand side, there is 1 magnesium atom, and there are 2 fluorine atoms. On the right hand side, we can also see that there are 2 sodium atoms. The number of fluorine in this case is 1. And the number of fluorine atoms is 2 times 1, which is 2. And notice that how every single of these are equal on both sides of the equation. Therefore, this indicates that this type of chemical equation is therefore considered to be balanced. Alright, we're now going to be looking at why do we actually need to balance a chemical equation. And the reason why that is because it needs to actually conform or obey or adhere to something referred to as the law of conservation of mass. So my first start point on this slide says all chemical reactions or chemical equations must follow this particular law over here. And the law of conservation of mass states that matter is neither created nor destroyed in a chemical reaction. So what does that even mean? So what this means is that mass is conserved so that the number, whatever you had at the beginning, say you had 10 grams, if you started with 10 grams, that means that by the end of the reaction, you should also have 10 grams as well. So the mass in this case is conserved. And the second dot point means that because mass is neither created or destroyed, this implies that there should be the same number of atoms of each element on each side of the chemical equation, meaning that the chemical equation is therefore balanced in this case over here. So just to show you what I mean by the conservation of mass over here, say that you started off with 100 grams in your reactants. At the end of the reaction, what you should also see is that you should also have 100 grams as well. So therefore, in this case, you cannot create something that is lighter or heavier than your initial amount due to the law of conservation of mass. Now, my first stop point again, I'm just emphasizing that all chemical equations or reactions obey the law of conservation of mass. And what this essentially implies is that all chemical equations need to be balanced. So in my example over here, the question reads, does this chemical equation correctly represent the formation of sodium chloride? So I've got the equation of sodium chloride over here. What I need to check is to see whether this chemical equation is balanced essentially. In this case over here, notice you've got one sodium atom over here on the left hand side, and you've also got one sodium atom, but you've got two chlorine atoms, but you've only got one chlorine atom on the right hand side. As a result, this particular equation is therefore considered to be unbalanced, and we can say that mass is not conserved since the number of chlorine atoms in the reactants and products are not equal to one another at all. Alright, it's time for you guys to check for your understanding. So remember, the law of conservation of mass states that your starting amount should equal to your final amount. This particular question over here wants you to find out what is the amount of zinc given that you know the masses of the other reactants and products. So give yourself 3 minutes to see whether you can answer this question, and afterwards see whether your answer matches my answer. Alright, now hopefully you guys answered this question already. So I'm going to be going over the question over here. Since we've already agreed that the law of conservation of mass states that the starting mass must equal to the final mass, what I'll do first is I'll calculate what is my total mass for my reactants. So if I've added 192 with 64, that should give me 256. Now, since mass is conserved, I would also assume that my products should also have a mass of 256 grams as well, because this is due to the actual law. Now that I know that the total mass of my products is equal to 256, and I know that the mass of my other product already, which is equal to 152, the way that I can calculate the mass of zinc is by going 256 subtract by 152, and as a result, the answer in this case is going to be 104, so C is going to be the correct answer. What I'd like you to do for the next 15 minutes is I'll also like you to please answer these questions over here. So some of these questions are just interpretation and also getting you to use the law of conservation of mass just to predict the masses of the products or reactants in this case. So give yourself 15 minutes. You don't have to write down the questions, but if you could write down the chemical equations, this would be very helpful though. And if you've done this correctly, these are the answers that you should have. So for the very first question over here, what is the mass of each reactant? So just simply state the masses in this case. What is the mass of the product? The mass of the product is going to equal to 80.6 grams. What is the sum of the mass of reactants? So sum means addition, so just add these two together. Now the question for the last question is does this experimental data support the law of conservation of mass? So in order to test in this case over here, what we do is we'll add up the masses of all the reactants. So if you do that, see whether that equals to 80.6, and in this case over here it does, since the reaction shows the mass of the products equal to the mass of the reactants case over here. And if you answer the other questions, these are the answers that you should have obtained. If you have any questions of how I arrived to these answers, please email me. We're going to be moving on to the next topic, which is how do we actually balance chemical equations. So you don't need to copy down anything on this slide over here, because this is just pretty much restating the things that you've copied down earlier. But the first dot point says chemical equations need to be balanced such that the equation follows the law of conservation of mass. This means that there's the same number of each type of atom on each side of the chemical equation. So on the right hand side on my little diagram over here, notice that these numbers over here are not equal to one another. These are not equal to one another. These are not equal to one another. And if this is the case, then this particular chemical equation is therefore considered to be unbalanced. So in this case, I've drawn that little scale over here just to show you that the total masses of each of these atoms over here are kind of more heavy on the left-hand side than the right-hand side. So we need to actually balance it. Now, in this particular example shown below, I'm actually showing you how we could actually balance the chemical equations. If you look at the speech bubble on the left-hand side, the way that we balance the chemical equation is that we need to actually insert a coefficient, meaning a number in front of the chemical formula, so that the number of atoms on each side of the equation is the same. So you need to add in a number in front of a certain chemical formula so that the atoms are the same. Now, we can clearly see that on the products side over here, there's one hydrogen less and one chlorine less. So we need to make sure that the numbers on both sides of the equation are the same. And the way that we can do that is we could actually add in a 2 in front of the HCl. But since this was actually lacking one hydrogen and one chlorine, by adding a 2 over here, this now changes the total number of atoms on the right hand side. Now notice if you do this now, the number of hydrogen atoms are now equal, the number of chlorine atoms are now equal. So therefore our chemical equation is balanced, and this is also diagrammatically or shown on the image down below. So as you can see, this is now balanced because you've got equal number of hydrogens, you've got equal number of chlorine atoms. So therefore, if you were to write down the full balanced chemical equation, it would just be H2 plus Cl2 with an arrow and then 2 HCl. As I said earlier on during this video, you don't need to include the number 1 at all in front of these because that's just assumed in this case. So any blanks or any numbers you haven't included, that means there's a 1 in front. So let's look at another slightly more difficult example over here. So in this case over here, this particular chemical equation is unbalanced, and what we want to do is we want to balance it. So in this case, I can see that there's only one silver atom on the left hand side. There is 2 hydrogen atoms and there's 1 sulfur atom. On the right hand side, we can see that there are 2 silver atoms, there's 2 hydrogen atoms, and there's only 1 sulfur atom. So in this case over here, there's the number of hydrogen atoms as well as sulfur atoms are balanced. However, we need to balance the number of silver atoms. In this case over here, notice that on the reactants, this is lacking silver atoms, so we need to add more silver atoms. So therefore, because we need to add more in the reactant side, we need to add a number in front of the chemical symbol that has or contains silver. In this case over here, this is where silver is, so we're going to add a number in front. So what we can do is if we added a 2 in front over here, this now changes the total number of atoms on my reactants. So now I have 2 silver atoms, and by adding that 2 over here, the number of silver atoms on my reactants now balances the number of silver atoms on my products. So therefore, this is the balanced chemical equation for this type of reaction. What I'd like you to do now, class, is I'd like you to please refer to the examples we just looked at so you can answer this checking for understanding question. I recommend you take your time and spend around 5 minutes to construct a table and count the number of atoms so that you can actually balance this correctly. So please pause this video right now so you can answer this question and then play once you arrive to your answer. So for this question, as always, we need to construct our table and list down all the elements present. We'll now start to count each individual atoms present. So on the left hand side or in my reactants, I can see that there is only 1 potassium atom. There is oxygen atoms for each of these reactants. So we've got 1 plus 2, so therefore there's 3 oxygen atoms in my reactants. There's 1 hydrogen atom, and then there's only 1 carbon atom as well. I'll do the same thing on the right hand side. We can see that there's 2. There is 4 in this case. There is 2 hydrogen atoms, and there's also 1 carbon atom. Once I've actually listed down and counted the number of atoms, I need to check to see which one is balanced and which one's unbalanced. So the only ones that's balanced is the number of carbon atoms. So I need to balance the number of potassium, oxygen, as well as hydrogen atoms. So let's just first start off by balancing the number of potassium atoms. Notice in this case over here, you've got 1 potassium atom on the left hand side and 2 potassium atoms on the right hand side. Since you've got you've got more potassium atoms on the right hand side, what you'll do is you need to add a coefficient on the left hand side so that the numbers are the same. Since potassium is contained within this particular compound over here, I need to add a number in front of that so I can increase the number of potassium atoms and make it the same thing as the potassium atoms on the right hand side. You should agree with me that the number in this case over here should be 2, and by doing that, I now have 2 potassium atoms. So therefore, these numbers are now equal or balanced, so this is now good. Now, you please keep in mind that by adding a 2 in front of here, you also change the number of oxygen atoms as well as the number of hydrogen atoms in the reactants. So by adding a 2 over here, this changes this, so now therefore the total number of oxygen atoms on my reactants is now equal to 4. So now this is actually balanced, and the total number of hydrogen atoms on my reactants is now equal to 2, and now this is balanced. And by doing so, now the number of atoms for each element is balanced. So this is the complete balanced equation for this particular reaction. Now, what I'd like you to do for the remainder of today's period is I actually want you to please answer these following questions over here. So please balance the chemical equations, and once you've done that, this is the answer that you should obtain with. And if you've got some time in this lesson, I'd like you to please answer this exit ticket that can be found in Google Classroom. There's just a few multiple choice questions. It won't take you too long at all. This is the end of today's video. Hopefully this video helped you. Please like this video if you enjoyed it. I'll see you in the next video. Bye.